The purpose of this lecture is to discuss the importance of everybody's favorite topic in chemistry, that being significant figures. Many of you have seen or heard information about significant figures from previous science classes, in particular in physics. So this lecture is mostly designed as a review of topics which you have seen at some point or another in the past. So let's just go ahead and jump in. The purpose of writing down data in science is to communicate information to others. And as such, the information which you write down and report needs to convey information not just about what you discovered, but also about the degree of certainty to which you know your data to be valid. And as such, we need some sort of conventions that allow us to convey to others how accurately we know the data which we are presenting. And those ideas are the ideas we refer to as significant figures. To give you an example of when this might come into play, imagine for a moment that you are an engineer and you are designing a, say, tank to hold some rocket fuel. And in order to design the tank, you need to make sure that it has a great enough capacity in order to actually get your rocket up into space. And say that in order to design the tank, the information which you know is about the density of the fuel which you are using. And so let's say you go by and you take a look at the density of that fuel, and to measure density, we calculate density by the equation from earth science days, density is equal to mass divided by volume. So in order to design this tank, you need to know how big it needs to be, and so you're going to go through and make a calculation of the density of your fuel to figure out exactly how large of a tank you need. And so you go and you measure some amount of mass of fuel, and let's say you use one of our analytical balances that we have here in the chemistry lab. Those balances are good to the 10,000th of a gram. And so let's say you go through here and you measure the mass to be, let's call it 100.0405 grams of fuel. And that's a very, very accurate measurement. As you can see here, we've recorded a lot of decimal places, all of which convey meaningful information about the magnitude of our measurement. So after making that mass measurement, let's say now you next go and you make a calculation of the volume of the fuel. And you measure the volume. But in order to measure the volume, the only thing you have lying around is a soda bottle. And you pour some of the fuel into the soda bottle and you see that it has a volume of, let's just call it, right around 100-ish or so milliliters. And in making that measurement, we really don't trust it really to any appreciable degree. We just kind of eyeballed it. It was as close of a guess as we could get, but really, we don't really trust that beyond really the one first recorded digit there. Somewhere around 100-ish, but it could be 85, it could be 134. We really don't know. And as such, we don't trust that information. So if we then take those two calculated values and divide the numerator by the denominator there, we would get an overall density that would come out to be 100.0405 grams per milliliter. And if we then recorded that information and supplied it to an engineer who is then going to go and design our fuel container based upon the density of our fuel, we'd have just provided him a number which fundamentally we don't trust. And we don't trust that number because even though we measured the mass incredibly accurately using a very, very, very accurate tool, we measured the volume using a completely garbage tool. And as such, the least accurate measurement that we made in making our calculations essentially determines the overall accuracy to which we know our answer. So giving him this final density of 100.0405 grams per milliliter seems like we're conveying more information about the accuracy of that number than we really truly actually know. And as such, we need some conventions to say which of those digits, which of those numbers that we just calculated do we really trust as actually being really true values. And those are the rules what we call significant figures. So we're going to kind of go through these rules one by one and talk about the logic behind why each one of them works, and then we'll take a couple of example problems to see how we apply these things. So, rule number one, when we're recording significant digits, every single number that you write down, which is a non-zero number, is by definition a significant number. That is to say, we don't just make up numbers to tack on to the end of our measurement to make it look more official than we otherwise actually calculate or measure. That is to say, we don't just write down numbers unless they were actually truly measured and reflect a meaningful value. So all non-zero numbers recorded are significant. So if I were to write down a number 1394 and record that information, each of those digits there conveys meaningful information. So we would say that that number 1394 contains 4 pieces of information or 4 significant figures. So rule number 1, all non-zero numbers convey meaningful information. They are significant. Rule number 2 has to do with what we call Oreo-O's. These are zeros that occur between other non-zero numbers. All Oreo-O's are also significant. So if I were to give you a number here which was 404, looking at the number 404 would convey 3 significant figures, because if the first digit conveys meaningful information and the last digit conveys meaningful information, the zero in between must therefore also be a meaningfully measured value. So in the number 404, we would say that there is a total of 3 significant figures. Now, you notice that the zeros tend to be kind of the problem in terms of counting significant figures. Since all non-zero numbers are significant, really it's the zeros we have to watch out for. So rule number 3 that we have on here is an important one, and this is one that people tend to forget about. Rule number 3 says that the zeros to the left of the first non-zero digit are never significant. And this might seem counterintuitive at first, because those zeros to the left sometimes look as if they're conveying information to us. Well, let me give you an example here. If we were to make a measurement of, let's say, 1 gram, I think we would all see very easily here that really all that conveys is one individual piece of information. That is one significant figure. So if there's one significant figure in 1 gram, if I were to convert that value from grams into kilograms, 1 gram expressed in kilograms is 0.001 kilogram. And by making a conversion from grams to kilograms, I didn't actually make my measurement any more accurate. I just changed the unit in which I was actually measuring. And as such, 0.001 kilograms conveys the exact same amount of information as 1 gram, which implies both of these only have one significant figure, one digit which conveys meaningful information. So the real idea is about those zeros that are to the left of the first non-zero number there, the 001 in 0.001 kilograms. Those zeros really don't tell me about the accuracy to which I've measured the value. All they tell me is, in this given unit of measurement, this happens to be a very small number. And small is not the same thing as accurate. Another way of looking at the same idea is to look at a number again, like let's say I count 37 of something. That conveys 2 pieces of information, the 3 and the 7. So there are 2 significant figures there. By putting zeros to the left of this, if I reported it as 0.0000037, I really haven't told you anything more about the number of particles which I counted there. So these zeros to the left of the non-zero numbers don't really convey information about the value. All they do is say that there's really no value in that place value. So zeros to the left are never significant. Last thing we have to deal with are zeros to the right of the last non-zero digit. The zeros to the right of the last non-zero digit would be in a number like, let's say, 300. In the number 300, we've got 3 place values here, and those 2 zeros to the right are the ones we have to figure out, because the 3 is by definition significant, since all non-zero numbers are significant that we record. So looking at those 2 zeros to the right, the real trick here is to recognize that zeros to the right of the last non-zero digit could have been rounded from another value. Like let's say the actual true value that was measured was 287, and we just rounded that to the nearest 100, which would be 300. That implies those zeros to the right really do not necessarily mean actually truly values of 0. They could have been some other number that just happened to be rounded there, and as such they do not convey meaningful information. So zeros to the right are not significant, unless I want to tell you explicitly that in fact those were measured zeros. So in order to show that in fact you had actually given a measured value of those zeros, to indicate that to a reader, we would write the number as 300 with a decimal place to show that in fact those were measured zeros. So the number 300 with no decimal place would be one significant figure, that is the 3, with the 2 zeros after it being non-significant, potentially rounded zeros. Whereas writing the number 300 with a decimal place after it conveys, in fact, those were measured zeros, and we show that again with a decimal place. So that would be a total of 3 significant figures in that number. So 3 sig figs for 300 point, 1 sig fig for 300. And those are our 4 main rules for significant figures. There's one additional rule that you're going to see come up from time to time, and that's the rule that has to deal with scientific notation. Scientific notation, as it turns out, is the easiest way to deal with significant figures, because when we write a number in scientific notation, let's call it 2.30 times 10 to the third, by definition, any of the digits which you write before the power of 10 in scientific notation are by definition significant figures. So 2.30 times 10 to the third would have, again, 3 significant figures. Or if I gave you 1.0 times 10 to the second, again, those two numbers right there, numbers that come before the power of 10, are by definition the significant figures of the problem, which would imply, therefore, we have 2 significant figures in that number. So that's all the rules for applying significant figures here. Let's now go ahead and take a look at what happens when we make calculations involving significant figures. And as we gave you for that example, when we talked about the calculation of the density of rocket fuel, the real trick here comes not just in terms of the measurements that we make, but the calculations we make from those measurements. Because when we make these calculations, we're manipulating our numbers, and we need to be able to report the degree of accuracy to which we know to be true about a calculated value. So just like when we talked about in the rocket fuel example, when we measured the density of our rocket fuel, that density was dependent upon the least accurate measurement that we made in order to make the calculation in terms of how much we trust the actual overall density calculation. That is to say, again, if we were dividing mass divided by volume to find our density, we again knew the mass to be a mass of 100 point something, let's call it 3047 grams. And then we said we had a volume of 100-ish or so milliliters. No matter how accurately I measured that mass, the overall density can't be reported particularly accurately because of the great degree of inaccuracy in our volume measurement. And as such, I don't feel safe reporting an overall density of 1.003047 grams per milliliter as a true and meaningful estimation of the actual value of the density of this fuel, again, because the accuracy of the measurement was ruined by the inaccurate measurement that we made of the volume. And as such, I would not feel comfortable reporting that I know this density to 1, 2, 3, 4, 5, 6, 7 significant figures as I've written down right here. In fact, I really only trust the density about as much as I trusted the least accurate measurement that we made, that was the measurement of the volume. And that measurement of the volume, 100 milliliters, only had one significant figure. That is the 1, because the 2 zeros that come after it are zeros to the right without a decimal place. So if I wanted to report the answer to the same degree of accuracy to which I made the measurements, I would therefore report that answer with only one significant figure, which means my calculated value of 1.003047 grams per milliliter, which I had written down 7 significant figures, really should simply be reported as 1 gram per milliliter. That would be reporting the one significant figure that we trusted based upon the measurements we made in order to actually make that calculation. So again, the general rule of thumb when dealing with a multiplication or a division is to round your answer to the least number of significant figures as the measured values you used in order to make the calculation possess. So that one's relatively straightforward, easy peasy. Let's see here, so that's multiplication and division. Last but not least, let's go ahead and take a look at addition and subtraction. And this is one that tends to cause people major amounts of headaches. As it turns out, it's also one that's going to be very important during the second semester when we move on to equilibrium chemistry. So we want to make sure that this is something we introduce to you now. We'll come back and kind of circle around to it again later. When we're dealing with addition and subtraction, the rules for multiplication and division don't make really any sense. Because if we try to apply them, let's say I went through and I was adding two numbers together, and I added together 1,025, and then I added to that 1. If I add 1,025 plus 1, that would give me 1,026. And if I was trying to apply the multiplication and division rules, remember the multiplication and division rules said that we were going to round this to the least number of significant figures that we had in our measured values. And that would, in this case, be one significant figure in that measured value of 1. So if I wanted to then try and round this answer to one significant figure, 1,026 rounded to one sig fig would give me a number of 1,000. And obviously you can see here that this answer makes no logical sense whatsoever, because taking 1,025 and adding 1 to it cannot give you a number which is less than what you started with. So trying to apply the multiplication and division rules to an addition or subtraction problem makes no logical sense. That really tells us then that we need an entirely different approach to dealing with addition and subtraction problems. So the trick is with addition and subtraction problems, what we're going to be focusing on is not the strict number of significant figures that are present in our measured values, but instead the place value of those significant figures. So let's take a look at an example here. If we make up a number here, and that number is so if we just make up a number here, and let's say that number is, let's call it 130,420 or so. And let's say I wanted to add to that number another value of, let's call it 22,000. If I were to add these two numbers together, and straight up just come up with a mathematical answer here, I would get values of 0, 2, 4, 2, 5, 1. So the sum of these two numbers mathematically is 152,420. But the trick is this. If we're talking about measured values in terms of significant figures, looking at my second number that I'm adding there, that 22,000, in 22,000 there are really only two significant figures. Those are the non-zero numbers, the 2 and the 2. The 3 zeros to the right there are zeros to the right without a decimal place, which implies they may have been rounded zeros. And as such, if those values really are potentially rounded zeros, that means that really I don't know what their true value actually is. So another way of writing this out would be essentially 130,420 plus 22 something something something. I don't really know what the actual value of those zeros truly is since they were rounded. And all of a sudden, this math problem becomes a little bit trickier here. The things on the left look easy. We have 1, 5, and 2. But then looking over the right, 4 plus a mystery number really is not necessarily 4, it's just a mystery number. Same logic for the 2. 2 plus the mystery number, I don't know what the answer to that is. So these place values, where I'm adding a rounded 0 to it, mean really I fundamentally don't know the value of that overall total. And as such, if I don't know the value of that overall total, I therefore would not consider those digits to be conveying meaningful information. That is to say, they are not significant digits. And as they are non-significant digits, that implies I should not record them as significant, which means I need to now show this problem, rounding it, giving only significant digits. So if I only wanted to record the significant digits in 1, 5, 2, and then 3 non-significant digits, the 4, 2, and 0 afterwards here, I would write that number out rounded as 152,000, and then just record these as essentially rounded non-significant zeros. So in general, the rule of thumb here for addition and subtraction problems is not to look at the total number of significant figures in the problem, but instead to look at where those significant figures are found in terms of what place values. And essentially just cut it off at the last measured place value where you have significant digits measured for each of your measurements. So in this particular problem, because the 22,000 did not have significant measurements in either the ones, tens, or hundreds place, I do not record those as significant figures in the overall answer. I only record the significant figures for the place values which have significant figures in all of my measurements, that is the 130,000, the thousands place, the 10,000s place, and the 100,000s place, which gives me my overall answer, as we said, of 152,000. So multiplication and division, just go ahead and record the least number of significant figures as in your measured values, but for addition and subtraction, record the place values in your answer, which have significant measurements on all the values which you've added together, and round the non-significant place values to zeros. So that's essentially the rules for significant figures. And now that you know how to do these, any calculations you make throughout the remainder of your year should be reported with the correct number of significant figures. So please get in the practice of doing so, since they will be showing up both on homework problems and on tests from here on out. And that concludes our discussion of significant figures for today.